and welcome back. Today we're going to do two advanced projectile problems, and I'm going to go through these fairly quickly considering we have already done the process a few times. So to start out, here is our first problem. A clown is fired at ground level from a cannon with a velocity of 18 meters a second at an angle of 65 degrees from the ground. He must land on a small cushioned platform that is 10 meters high. How far away from the cannon should the platform be placed horizontally? All right. For starters, I know I'm going to use my table, so I'm going to put that on the page right now. So, first step, let's draw the situation. Here's my cannon, fires the clown, and he needs to land on the platform. We are looking for delta x. How far horizontally should the platform be placed? The platform is 10 meters high. Here's my initial point, here's my final point. 2, let's split up the initial velocity. Initial velocity is 18 meters per second at an angle of 65 degrees above the ground. Here's the split. This is VIX and this is VIY. Using cosine, VIX is 7.61 meters per second, and using sine, VIY is 16.3 meters per second. I'll put that in my givens list right now. Since acceleration in the x is 0 meters per second squared, VFY is also 7.61 meters per second. Acceleration in the y is negative 9.8 meters per second squared due to Earth's gravitational pull. And there's one more given I know. If this is the initial point and this is the final point, then that means my displacement has to be positive 10 meters because a clown has to end up on the platform. Now, there was one more part of the technique where I suggested that you use the picture to put in any negatives. I'm going to skip that for now, just to show you why it's very important. So the question is, how far on the x-axis do I need to place this platform in order for the clown to land on it safely? My x-axis is pretty useless here to find it, so I'm going to start on the y-axis. I'm going to go after VFY because it's really easy using this fourth kinematic equation. Rearranged, VFY equals square root VIY squared plus 2AY delta y is 16.3 meters second squared plus 2 times negative 9.8 meters second squared times the 10 meters. Under the radical, 256 meters second squared minus 196 meters squared over second squared. Oops, it's meters squared, which will give me positive or negative 7.75 meters per second. So which one is it? Well, looking at my drawing, the clown is on his way down when he lands on the platform. That's the only way he could land on it. And this is actually kind of key. So I recommended as soon as the picture is drawn, and knowing he's on the down arc in order to land on the platform, this negative should have been put in right away. Because if I left this positive, that means I'd be placing the platform on the way up. So the clown would not land on the platform. You'd be slamming his face into the bottom of the platform, which would really be no good. So VFY is negative 7.75 meters per second. Now I can get time. VFY minus VIY over AY. I'm using the second kinematic equation. Negative 7.75 meters per second minus 16.3 meters per second. So if you notice, keeping this as negative is making this time increment larger. Otherwise, these would be a smaller number. Otherwise, these combined would create a smaller number over negative 9.8 meters per second squared. These negatives all cancel. The meters cancel. One of the seconds cancel. I get 1 second. I get one of the seconds left, and I get 2.45 seconds in here, which means I can get delta x using the third kinematic equation. Delta x equals VIX times time equals 7.61 meters per second, 4 or 5 seconds. Seconds cancel, and I get 18.7 meters. 18.7 meters is my answer. It's how far away. So this was not a perfect arc. There is no symmetry here. So I couldn't just, make VFY the opposite of VIY here. I actually had to find it. And it all really comes down to understanding your image in the beginning. All right, let's do one more. A baseball is hit when it is 1.5 meters above the ground. It leaves the bat with a velocity of 35.8 meters per second at 55.7 degrees from the horizontal. The outfield wall is 6 meters high and is 118 meters away from home plate on the horizontal. Is the hit a home run? And by how far is the ball above or below the top of the wall at that point? So, again, I'm going to put my table up there immediately. The ball is hit 1.5 meters above the ground, goes into the air, and there's a wall. I'm actually going to erase this because we don't know how high it goes. That is 6 meters high. We don't know if it hits the ground, hits the wall, or goes above the wall. So let's put a pin in this for now and think about it when we make our givens. This again was step 1. Step 2, let's break up our initial velocity vector. This is 55.7 degrees, and this is 35.8 meters per second. Using cosine, 20.2 meters per second on the x. Using sine, 29.6 meters per second on the y. Put those in right now, 20.2 meters per second. So will the final acceleration on the x-axis is 0 meters per second squared. I'll put in the y right now as well, negative 9.8 meters per second squared because we are on Earth. VIY, positive 29.6 meters per second. Okay, here's the deal, and this one's a little different, and it's why I chose it. Remember our earlier questions? What are you tracking? When does the problem start? When is the problem over? Well, we're obviously tracking the baseball. Problem starts when the ball is hit. I should put those in here, actually. Initial point. When are you ending the problem? Notice I didn't put my final point in. So the wall is 6 meters high, but I can't put that in my givens list because that does not track anything about the ball. I have no idea if the ball is going to make it 6 meters high when it's at that point. That's what the question is asking. In other words, that's information about the wall. It's not information about our target, so it does not belong in this givens list. However, I do know if the ball has made a home run if I make the endpoint this line, which is 118 meters from home plate. In other words, the math does not know that the ground is here. So forget this. If he misses and hits the ground, I'm going to know because it's going to give me an ending problem here. In other words, the 3 possibilities come to this. Ball could arc and be really short. The ball could arc and hit the wall, or the ball can arc and go over the wall. And if I make my delta x the 118 meters, I will know if it's a home run or not depending on what delta y is. So in other words, this problem is different because my better information is on the x-axis this time, which is pretty rare. And the question comes down to, when is the problem over? For a lot of problems, it's over when it, say, hits the ground. That is totally dependent on the y-axis. For the last problem we did, when the clown landed on the platform, that was also totally dependent on the y-axis. For this one, this problem is dependent on the x-axis. Where is the ball when it's 118 meters on the horizontal? And again, the math does not understand the ground is here. So if I get negative 30 meters for my answer for delta y, I'll know the ball wasn't even close to getting a home run here. Now, part 3, I'm going to fill in my givens table until I get what I'm looking for. I'm going to start with the third kinematic equation because on the x-axis, acceleration is 0, which means delta x is Vix times time. Time is delta x. Delta x over Vix is 118 meters over 20.2 meters per second. Meters going to cancel. This is going to flip. I get a time of 5.85 seconds. Take that, put it in my table. 5.85 seconds. I want to know how high the ball is at this point. Can I do it one shot? Yes, I can, because I can use this third kinematic equation again, this time on the y-axis. Delta y is VIY times time plus 1/2 AY delta t squared is 29.6 meters a second times 5.85 seconds plus 1/2 times negative 9.8 meters a second squared times 5.85 seconds. This is squared, gives me 173.16 meters minus 167.7 meters gives me 5.47 meters. So delta y is 5.47 meters. Was this a home run? If I look at this right now, it looks like no. However, we need to remember one more thing about the problem. The baseball is hit when it was 1.5 meters above the ground. And this list tells me this information in relation to my initial point, which is 1.5 meters above the ground. So in other words, this delta y is above where it was hit, not the ground level itself, which means if I add the 1.5 meters, I get 6.97 meters from the ground, which means he makes it by 0.97 meters. It is barely a home run. It's a home, he made it by 1 meter. Okay, so I just wanted to show you how important those original questions are. And for the clown one, the fact that you need to recognize what direction the final velocity is in, because using that fourth kinematic equation will give you both a positive and a negative when you're solving for VF. This one was important because all the good information was on the x-axis. And again, I could not use 6 meters for delta y because I was not tracking the ball. I had to use the x displacement 118 meters and see where the ball was at that point. All right, for anyone who would like a bit of a challenge, I have a question for you. A rocket is fired horizontally from a 2-meter high table. It leaves the table at 30 meters a second and has an acceleration of 50 meters seconds squared due to its thruster. Its fuel lasts for 3 seconds. How far away from the table will it hit the ground? The rocket stays horizontal, so the acceleration from its thrusters are only on the x-axis. How far away horizontally will it hit the ground relative to the table? Give it a shot. The answer was at the beginning of this video in the lower right-hand corner. Good luck. Have a good day. This is Mr. M signing off.